Hello, everyone. This is Tom Ballard, the Groundwater Guy, here with another edition of Groundwater Talk Live. Today, we're going to be talking about traditional zone testing versus well profiling, and so this is a topic that has engendered a little bit of interest. I know I work with some engineers who are absolutely insistent that the traditional zone testing is what they want to do, and because that's the way it's always been done. But we do have some different methods out there. We'll talk about the pros and cons here today, and as we get going, excuse me, got a little bit of allergy issues here. So let's, before we get going, if you got any comments, post them in the comments below. And, also as we go along, if you have any questions, please post them in the chat, and I'll answer them as we go along. I'm kind of a nonlinear thinker on these things, so asking questions certainly does not interrupt the process at all. So I'm more than happy to get your questions, and at the end we'll have some contact information for you. And if you have any interest in or suggesting a show topic you'd like to see, let me know. A lot of our show topics come from people that have interest in a particular topic, and we'll put together a little show on that and answer some of their questions that way. So, all right, so let's dive in a little bit here. And before we really talk about zone testing and its alternatives, let's really look at the well construction process and where zone testing really comes into play in this process. So here's basically a simplified outline of the well construction process, and we start with our test boring. We're going to go through our whole well location siting study and that type of thing. And then we're going to go out and get our permits and drill our test boring. So once our test boring is done, we're going to go in, we're going to do our geophysical logging. We're also going to probably do, and I highly recommend doing geologic logging during the drilling of the test boring. And then after the test boring is done, go in and do geophysical logging. So we're going to take our geophysical logs and our geologic logs, and then we're going to go in and we're going to do some zone testing or well profiling, as the case may be. And we'll look at the alternatives here today. That's the topic of our show. Then based on that information, we're going to do well construction, and then finally on to development and pumping tests. So that's really a simplified outline of the well construction process. Obviously, there's a lot more smaller steps that go in there too, but this kind of gives you an idea of where the zone testing actually fits into things here. So what is zone testing? Before we dive into all the mechanics of it, what really is it, and what do we get from it? So obviously, if you're drilling an alluvial aquifer, for instance, we're going to have aquifer zones. We may have one or more aquifer zones. We want to isolate those specific aquifer zones to test for both flow and water quality. It's going to help us in our well design is really what it comes down to. But we want to look at both flow and water quality, and we're going to isolate those zones. So that's really what zone testing is. We're going to look at our geophysical logs and our geologic logs, and then we're going to select zones for testing based on those logs. And so obviously it's a little bit different if you have a fractured bedrock aquifer. You're really looking for the fracture zones, and those are the ones we're going to try to test individually as well, because that's going to be your productive zones in a fractured bedrock well. In an alluvial well, you're looking more at your sand and gravel zones, and looking at the specific aquifers, as it were. And like I say, we may have one or more. For instance, in the Central Valley of California, you're usually going to have 2, 3, 4 different aquifer zones, and you're going to want to zone test those so you know not only what the water quality is coming from those particular zones, but do we have any issues with the water quality? You want to know the flow. So I misspoke here. So you want to know the flow from those zones because it's important. We want to achieve a certain production goal, but we want to know the water quality too, because if we have poor quality water, then there's certain things we can do to modify the well during the design phase to deal with that. Or it'll give us a heads up if treatment is required. So that's what we need to know, and what are those specific zones. So that's really what we're looking at. And our zone testing will dictate our final well design. So if we have some zones where we have unacceptable water quality, we may decide to seal those zones off, or as we do a mass balance, we may determine that those zones are diluted down enough that we don't have to deal with anything, or maybe low-level treatment. So this is really an important part of the process in the well design, is what zones do we want to take? What aquifer zones do we want to take, and construct our well around that? All right, so, and typically here's kind of a simplified borehole geophysical log, and you can see here we have some freshwater zones, some high TDS water zones, or what salty water, and we're seeing spontaneous potential on the left, resistivity in the middle, and gamma. Those are going to be your typical E-log types of responses, and we're going to see that the resistivity is kind of our guide, and the gamma is our guide here. So the freshwater zones there are really what we're going to want to probably at least preliminarily take. The geophysics may tell us that we have some high TDS water, that's salty water zones. So we may want to actually go in and test those during zone tests to see how bad they really are, and to see if maybe we can take those zones and the flow and the water quality is sufficient to actually dilute that down. So in this case, we may look at testing 5 zones in this well. So we want to isolate those zones and test them. We may know already that we don't want to take some of those things, so we may not take those salty water zones and test those. We may just want to test the freshwater zones there. So that ends up being a decision based on the geologic log, the geophysical log, and probably some your knowledge of the area itself. I mean, one of the things we do during well siting studies is we look at other well logs and see what problems they've run into, and see if we have any heads up on water quality issues. But in this case, we may want to actually go in and test all 5 of these zones and run some mass balance and determine if it might be worthwhile. If we get enough production out of these some of these salty water zones, and the concentrations are low enough, it might dilute down where we can take those zones and not have to worry about treatment. So the geophysical logs and the geologic logs, like I say, are our guide for determining what zones we're going to isolate for our zone testing. Okay, so for doing our test well evaluation, we have a number of options, and we're going to be looking at our traditional zone testing, and that's kind of what everybody's done all along. That's building a well within a well, and actually building little miniature wells, and like some engineers that I know, they really love doing this stuff, but it's kind of out of date stuff. There may be some reasons for doing it, but I think there's some better methodologies. Packer testing is something that we'll look at here. Packer testing is using inflatable packers to isolate zones. That generally works best if you have a fractured bedrock aquifer and you're looking at isolating specific fracture zones. It's something where if we go into an alluvial well, you really have to trust that well is going to stay open for running those packers in and out, and so I consider it kind of risky, because this straddle packer setup you're going to use can be expensive, and you don't want to bury it down there and lose it and have to go in and drill everything out. That gets expensive. And then finally, we're going to spend most of our time actually talking about well profiling, because there's some different methodologies there and some tools that we use for that. So we will look at that as well. All right, so this is basically a schematic that we drew up for a well in Southern California. Essentially what we're doing with zone testing is we're looking at our geophysical and geologic logs, and I don't have the geologic log on here. We just have the geophysical logs. But we're going to build a series of wells to isolate and test specific zones here. And in this case, we identified really 3 zones that we wanted to test. So we go down to that lower zone. You can see on the resistivity, so that's the farthest right of the geophysical logs. You can see we got a bump in the resistivity that indicates we probably have some a decent water bearing zone. So we wanted to go in and test that. And then what we do is we put fill in that zone, and then we go up to the next one. So there's a zone in there from about 200 to 250 that we'd want to look at isolating and test that zone. And then what we would do is we would pull all that stuff out, and then we'd go up and we'd build a third well within the hole. We'd put fill down below, and then we go up and test that third zone from about 100 to 150 feet. There, we got some resistivity response, and we test that zone. So, as you can see, now we have to go back in after we've done this, and we need to ream everything out and vacuum out all that fill material and the bentonite and everything that we put in there. This can be an expensive and long process to do this. So the other thing is you're not really able to fine tune things really well. So you're going to test an entire zone at a time. Really, 3, maybe 4 zones is kind of your practical limits because it starts to get long and expensive. So that's really what that looks like. So with traditional zone testing, it requires that we build a temporary well for each zone to be tested. So we usually start at the bottom, and then we're going to go and we're going to pull out each well, and then we're going to do some fill, and then we're going to put some bentonite down. We're going to put a sand layer and a temporary screen in there, and then another, and then sand layer, and then some bentonite on top of that. We're going to put a pump in, and so we're isolating that specific zone. Next one, we're going to pull that out, and then we're going to put fill in, and then we're going to build another temporary well in the next zone we're going to test, and then we move up. So we don't start at the top and go down. Of course, we start at the bottom and go up and test the zones from the bottom up. And as you can guess, this can be expensive and time consuming. We're going to put a lot of fill material in there and bentonite and all the materials to build all these temporary wells. And then at the end, we're going to have to go in and pull all that stuff out and ream the hole and pull everything out. And you're going to have a bunch of wasted material that you put down there. So it can be expensive, but the main thing is very time consuming, and time is money. So we definitely want to look at that. And then we have limited flexibility with this. Obviously, you don't get the granularity that you might with well profiling, and we'll look and see what that looks like here in a little bit. So you're really testing broader zones, usually 20 to 30 feet at a time. And so you're not able to get that really granular look-see at things and really subdivide some of those zones. And so otherwise it would be hideously expensive. So limited flexibility, which means that you may not dial in your well design exactly right because you're testing some wider zones there. So limited flexibility with traditional zone testing, but like I say, there's a lot of people out there that really believe in this, and that's how they've always done things, and that's how they always will do things. And I believe there's some better ways, and I go round and round with them, and we're making some progress on selling people on the well profiling, but sometimes it's slow because in this business, as you well know, we certainly get a lot of traditionalists out there that want to do things the way they've always been done. All right, so packer testing. This is another method that we use. Best in fractured bedrock environments. Requires a stable borehole. So oftentimes not good if you're an alluvial well. And we have had incidences where packers can get stuck in the hole, and then you do a bunch of damage trying to get them out. So there's no guarantee they're going to go in and out very, very smoothly. Sometimes they just don't deflate like you expect them to do. So a packer is really an inflatable. It's usually going to be some kind of thick, rubbery substance. It's going to be able to take a lot of air pressure, and we're going to pressure these things up so they get a tight seal against the borehole wall, so that we can isolate specific zones. And the trick is generally if you're going to run a packer test, you're probably going to want to run a caliper log, so you don't try to inflate your packer across a zone where you're going to get where there's existing fractures and where you don't get a good seal with that packer. Otherwise, you're going to have a leaky packer zone, and it's going to interfere with your testing. So very, very important to make sure that you get a good seal with the packer, and that's kind of one of the little tricks with doing packer testing. All right, so this is another schematic of actually how that works. We're going to go down there. We're going to have our upper packer, our lower packer. Obviously, if you're in the very bottom of the well, you'd use a single packer. This is basically your typical packer testing schematic. So we have our straddle packer here, and then we're going to have our isolated interval. So this is a limitation of the straddle packer setup, is because it's hard to adjust for the amount of screen you have. So you're probably going to do a standard like 5-foot interval, or you're going to have to determine that ahead of time. So that can be kind of challenging. If you go to the bottom of the hole, if you're at the bottom of the hole, you may only use one packer to isolate that zone. But anything above that, if you're isolating zones, it's going to be a straddle packer setup. And then you can have your pump will go down that drop tube in the middle, and then your screen is going to be in the zone you're isolating. And that's basically what we are going to test. And then you will, once you're done with this zone, you will deflate the packers and move them to the next zone. And obviously in this case, we can, it's generally better to go from the bottom up, but you can kind of move these around as you see fit, especially if you're in a fractured bedrock hole. If you're trying to do this in alluvial aquifer, you really want to make sure you have a very stable borehole, and I would start from the bottom up, just to make sure that you're moving your packer out. As you inflate and deflate these things, you may destabilize your hole. So that's something we want to look at. All right. So the other thing you can do with packers in a fractured bedrock aquifer is we can do, if you have multiple wells that have interconnected fractures, you can actually isolate the fractures and do cross-hole testing. And this can be helpful in contamination studies, is to look at the flow through the fractures between different test borings or even different wells. We can isolate these zones and do the cross-hole packer testing. So this gets done a lot in contamination studies, not so much for water wells. We're generally basically just interested in our productive fractures. So if we're looking at contamination, yes, these types of studies are good, because you can have different fractures and different orientations that are going to, the contaminants may move through certain orientations of fractures and not others. And so it's important to identify what those fractures are and their geometry in order to treat the contamination. So we see this type of packer set up a lot in fractured bedrock where you're evaluating contamination. All right. So well profiling methods. We're going to get on to well profiling, and there's really a number of ways to do well profiling, and that's what we're looking at here. So first of all, we have a spinner flow meter, and I'll look at each of these in turn here. I'm just doing the list here. A heat pulse flow meter. That works pretty much like you'd expect. Electromagnetic or EM flow meter, and then dye trace methods out there too, which aren't flow meters at all. And I'll show you how that works as well. So before we get into those, there's two types of testing we're going to look at doing. There's ambient testing and dynamic testing. Ambient testing measures the natural flow into the well under non-pumping conditions, and this is going to be important to determine how things are flowing into the well when we're not pumping, so your natural state of things. Usually any of this testing is going to require removing the pump. The ambient testing, so we can have free access to the well, you're going to remove the pump, and then we can take our meters up and down the pump. The problem is if ambient flow is really low, we may have to do something like a colloidal borescope, and it gets a little trickier that way. So certainly if there's low flow conditions in the well, under ambient conditions, a spinner flow meter is not going to work. And if it's below the range of an EM flow meter or heat pulse flow meter, then you may be looking at a colloidal borescope. And that's a specialized piece of equipment not everybody has around, and so it can be difficult to evaluate these things if the ambient flow is low. Probably more of concern to us for our well design is dynamic testing, and that's going to measure the flow into the well under pumping conditions, which means we're going to do this testing while there is a pump in the well and it's actively pumping. So it most accurately simulates well production in terms of flow and chemistry from the individual zones. A little more challenging to perform because you need to take the pump out, you need to put in the tool you're going to use to measure things, you need to put the pump back in, and then do your testing. You can't pull your tooling above the pump, so you have to place your pump appropriately. So that's going to be a little tricky. But if you have an experienced operator, they should be able to get you all the data you need. And obviously, it's going to require multiple trips in and out with the pump. So that can add some cost to things, but that's a normal part of the process. So with dye trace, sometimes you can do it with the pump. Leaving the pump in, but not always. Sometimes it's hard to thread it down there. So even though they say they can always do that, my experience has been that it's 50-50 on that. So where it works, it's great. Where otherwise you're pulling the pump and doing the exact same thing you would for like an EM flow meter. All right, so these are the individual types of flow meters. This is a spinner flow meter, also known as a propeller or a spinner, and it's got a little propeller in there, and that propeller is going to be spin based on the flow of the water past it. So obviously the greater the flow, the faster it's going to spin, and so you're going to get basically a reading in counts per second that you're going to need then to interpret and to get to the gallons per minute in that specific zone, and so we'll run these things up and down so we can compare the readings going down as well as back up, and you're going to get kind of a continuous log. There is a heat pulse flow meter. The way a heat pulse flow meter works is it releases a heated burst of water below, and then it uses a diverter to have the water flow up through. So the time from when that heated water is released to the time it's detected above the flow meter or above the diverter, then helps determine your flow rate. Once again, some interpretation is necessary on the time to convert it to gallons per minute. The electromagnetic flow meter, this is one view of that. It's going to have a diverter skirt also. It operates according to Faraday's law of induction. So there's a voltage induced across the conductor, moving at right angles through a magnetic field proportional to the translational velocity of the conductor. Water is the conductor in this case. So you have to have conductive water. What happens here is that It operates the same way. If you have flow meters that don't have dials and paddles on them, then you're probably running an electromagnetic flow meter on your piping and your distribution lines, and it works pretty much the same way as that. But just know that it's a standard type of Faraday's law of induction, and so this is a tested and true method and very reliable bit of instrumentation. Both electromagnetic and heat pulse flow meters can evaluate vertical flow rate in up and down directions, so not just inflows, but flow rates up and down. And normally in wells, we're going to get some component of vertical flow, so they can measure that. They have an accuracy of 0.1 to 1.5 gallons per minute when used with the diverting skirt for stationary readings. And so fairly good accuracy there. The electromagnetic flow meter, more effective due to its trolling capability for continuous data output, which means we can put that probe down to the bottom of the well and pull it up very slowly, and it's going to continuously log the hole all the way up to as far as we can bring it out. So the range of flows these can measure 1 to 2,000 gallons per minute. So a fairly wide range on both these tools. I tend to prefer the electromagnetic flow meter just because it's got so many positive facets to it that we get a lot of good data with it, and it's reliable data, and it's almost continuous data. So we can get some very detailed analysis of the flow conditions in the well with an EM flow meter. And then there's the dye trace method, which actually uses a dye injection in the well. That's going to be a fluorescent dye. It's going to be during pumping conditions. You're going to inject the well or the dye at a certain depth. The well is going to pump that up. It's going to come out to a fluorometer, and it's going to read the first arrival of the dye because it's a fluorescent dye. And then you're going to do your calculations to determine what your flow rate is in that particular zone based on the diameter well, the pumping rate, and how quickly it takes to get to the fluorometer. So the trick with this is you're not going to get, these are usually kind of either 5 or 10 foot increments is what we're going to do here. So you don't get the granularity that you would with like an EM flow meter and the continuous logging. This is a little bit more time consuming for a bigger well. It can take several days to do this. So it works pretty well with the calculations, but it can be a lot more time consuming. And the big promotion on this is that you can install these things and run it with a pump in the well. That's not always true. We see a lot of wells where the pump bowls are so tight that you can't thread down past them, and so you got to pull the pump anyway. So, and that happens in a lot of cases. So my experience is, generally 50% or less of the time you can get down there without pulling the pump. But where it does work, it works pretty well in that regard. All right, so back to our EM flow meter. This is what the whole tool looks like. It's going to have all the electronic equipment on board, and the lower port, the upper port are down below there. There's going to be your flow diverter skirt down below. There's going to be some centralizers there to keep it in the middle of the hole, and so there's a lot of electronics packed in this tool. So they're going to run it down, and they're going to go to the bottom of the well, and they're going to pull it up at a steady speed and do continuous trolling. And so you're going to get a pretty much continuous log of the flow characteristics of that well from the bottom up. And I'll show you what that looks like towards the end of our talk here today. This once again is showing how it operates according to Faraday's law of induction, and so this is kind of an example of a flow meter that you'd put on your pipe from your pump to your distribution system to totalize your flow or to see what your flow is. the electronic flow meter works the same way going down the well. So it's using water as the conductor, and it's measuring the inductance across the flow profile. All right, moving on here. Let me grab a drink of water here. Okay, so our well profiling procedure, what we look at is after we drill our test boring, we're usually going to thin the mud down somewhat so we can go in and do our geophysical testing, but you're going to need to thin things out and clear the test boring of mud and turbidity before you can do your well profiling with with any of these meters. And probably the dye traces as well. You're going to install a temporary screen then if necessary. If you're in a fractured bedrock environment and you have stable boring, this may not be necessary, although we've seen it sometimes where we get caving and stuff. We will actually install a temporary well screen. Pretty much required if you are in an alluvial aquifer. We don't usually build a well. We just use the temporary screen, so we won't necessarily put any sand pack around that. We'll just use the temporary screen basically to hold the hole open while we do the testing, because we're going to be pumping and we just don't want that hole to cave in and then we got to go back to the drawing board. So then we're going to conduct our ambient testing. We're going to install a test pump after that and then conduct our dynamic testing with the test pump in. So we're going to install our tooling. We're going to put in the test pump at our selected depth, and then we're going to do our testing, and then we're going to pull the test pump out and pull our tooling out. So we are going to then collect depth discrete water quality samples under pumping conditions so that we actually take those samples and cross-reference them with our flow profiles so we can do a mass balance and determine where our highest flow zones are, where our water quality issues are, and see what zones we may need to seal off and if it's worth it to seal it off. So and then we'll analyze our data and design our test well accordingly. So it's really going to be based on the data. And remember, of course, that our selection of zones and our interpretation of the zone test data or the well profiling data is going to be based on our geophysical and our geologic logs as well. So that's going to be our starting point, and then all this actually flows from that. All right, so just some examples here. This is actually a USGS arsenic evaluation somewhere in California. I don't remember exactly where this is right now, but you can see on the left, starting on the left, we have spontaneous potential, or SP. The green line there is lateral resistivity, and you can see that our most productive intervals, according to the resistivity, are up above. We get a little bit coming in down below, and that's also reflected in our SP, which is more of a gentle swing. SP doesn't do really dramatic swings like the resistivity does. And then in the middle there, moving over, that is going to be our borehole flow. In this case, it's liters per minute. And we can see that most of our flow, some of those zones down below contribute, but really when we start getting up in that zone that's shown on the resistivity, where we start getting a lot of high resistivity, that's going to be our productive zones. And you can see our well discharge, our flow rate is actually stepping up right there. So we got some specific zones we're encountering there. And then the next one over, we're actually looking at our arsenic concentrations. So obviously our arsenic samples, we don't sample those as frequently as we do with the borehole flow meter, because you're getting almost continuous. We're going to have to collect the arsenic samples or any water quality samples at discrete intervals, and then kind of fit those in with our flow profile. And then off to at the far right here, then we have our geologic log, and we're kind of playing that out there too. And you can see down below, you can see some of these lower resistivity bumps are actually in thinner sand zones there, so that's pretty much to be expected. So there's some yield from those zones that we can see in our flow profile. So you can see how we really kind of put this whole thing together. And this is a USGS examination. I got some examples of some testing we've done using well profile that I'll show you here at the end. Our well profiling procedure, we've already looked at that. Sorry, I got that in here twice. Boy, what did I do? I put things in here twice. I went the wrong direction. So, assessing saltwater intrusion. Here's another study that the USGS did in California. So you can see over here on the left hand, going from left to right, on our left hand side, we have our resistivity. Once again, we can see where our productive zones are based on the resistivity. They have individual aquifers marked here, and that's based on the geology out there, and then also the resistivity logs. So you can see the breaks between the different aquifers, and then we move over and we look at chemical concentration. This is actually going to be the dark pink there is going to be chlorine, and then at two different intervals, and then the orange there is going to be sulfate. So the chlorine is really what we're concerned with, and then we have to the right we have a spitter flow meter log. And then in this case, they were actually using dye trace to look at this. The dye trace method was originally developed by the USGS. It's used by another company out there. Now they've licensed it from the USGS. They got an exclusive license, I believe, but it was originally USGS technology, and they still use it. And so we can see those correspond. Those two flow meter logs actually correspond with each other quite nicely. So that's all well and good. And now, so we can make some decisions here. We go back and look at our wellbore chemical concentrations, particularly the chloride. We see starting kind of at the bottom of the Fox Canyon aquifer, but into the Grimes Canyon aquifer, we see a high chloride concentration. So those zones are dealing with saline water, and that's reflected more in the muted resistivity as well. But if we compare that to our flow meter log, we can see that most of our flow is coming from the Fox Canyon and the Hueneme aquifers. Not much chloride up there. So we could actually, this is actually a good test. We could actually take this well, and if we hadn't actually put in a well yet, we could actually design the well so that we're not really taking anything. We would probably develop our well kind of partway into, maybe a quarter of the way. We'd seal off the bottom of the Fox Canyon aquifer and all of the Grimes Canyon aquifer. So we just take things above that, because then you're going to get clean water and you're going to get your best flows. Literally no flow at all coming from the high chloride zone down deep. It's stagnant, salty water. So we don't want to take that anyway. So this shows the value of that. And this could really be any type of contaminant, for instance, where this is just a handy dandy USGS study that I had and wanted to show that to you. So here's another example. This is This is using the USGS Analyze Well tool software for looking at arsenic concentrations and hydraulic conductivity. So we can see on the left-hand side here, we're looking at hydraulic conductivity is the black blocks there. The geology is kind of superimposed there. So we have a silt up above. We have a clay. We have a sandy zone, a gravelly sand, a clay and sand is the blue there, and so on and so forth down below. And then if we look over to the right, now we've done our well profile, and we can see where our screen zone is the black blocks, not the outlined ones. That's on the left, that's the hydraulic conductivity, but on this side we look at the screen intervals, which are appropriately screened in the sands, and we see that our highest arsenic is down below. We got 15 parts per billion down kind of in that lower zone, and 5 parts per billion up above. So obviously 10 is our MCL, but there's very little flow down below in that lower zone where it's screened. So we would probably want to take those upper screen zones that are plotted there and seal off the bottom one, and you're likely going to be below the MCL for arsenic. In this particular case, you might have diluted things out enough with the flow from up above because you really don't have much of the high arsenic flow coming into the well. But just to be safe, I would design this well so that we didn't take that lower zone at all and we didn't have to mess with that. And then we stay well below the MCL for arsenic. So that's an example there. Now, sample collection methods, there's a number of methods we use, a gas displacement pump, pressurized baler, snap sampler, hydrosleeve, passive diffusion balers. The problem with things like those last four from the pressurized baler down below, these methods really limit the amount of sample you can actually collect. If we're running for a full suite of water quality parameters, you may not be able to get enough in a snap sampler. I know you won't. Hydrosleeve might be the same. Passive diffusion balers, mainly used for volatile organic compounds, so generally not too relevant to our situation. So we're going to be looking at either using a gas displacement sample pump, and that's what's shown on the right-hand side there. That's a USGS design that I believe is also licensed out now, and it's a really small one. It's designed to fit down a well and thread it past the pump. Not always the case again, as I mentioned earlier with the dye trace, but it is fairly small diameter. It does have some limits how much you can sample at a time. So any of these things you're going to have to work at them a little bit. We tend to probably use a pressurized baler. It tends to be a little quicker, even if you need to make multiple runs down there. But the gas displacement pump certainly is a viable alternative as well. The other ones, if you want limited quantities and you're looking at really environmental samples, then those are probably going to be okay. Otherwise, for general water quality and testing for test wells that are going to be used for drinking water purposes, probably the top two, the gas displacement pump and the pressurized baler, is what we're going to use. Also, just want to mention, generally these samples we're going to pack up, we're going to put them in laboratory-approved containers and ship them off to the lab, but there are a number of field test kits out there. Here's an arsenic field test kit, but there's a lot of them that are available. Some of these will actually plug into your iPhone so you can record the readings and GPS the location, and so you got some pretty fancy and sophisticated tools for doing testing on site to give you an indication of what's going on as you're going along, so you don't have to wait for laboratory turnaround times. These can be good, and the accuracy actually of these things is getting pretty darn good. It's still not laboratory quality. It's not a certified lab test, but it's certainly something that we can look at and do some screening in the field and help us make some field decisions right then and there. So I would urge you to look at these. We've used these in the field a lot, and it can provide just real-time data, all near real-time data. Arsenic takes about 12 minutes to run, so better than waiting, even with a quick turnaround time, waiting for 2 or 3 days to get samples back from the laboratory. All right, so flow calculations. With our continuous flow meter logging, we can break these into zones and kind of, we'll have a continuous log, but sometimes for the purposes of doing a mass balance, we're going to want to break these out into zones. And there's probably going to be distinct zones that are going to be defined by your flow, breaks in your flow, and your resistivity and your geophysical logs. So that's going to be something we're going to look at is what specific zones are we going to look at, and then we're going to match up our sampling results to those zones and make some decisions about these particular zones. Are we going to screen them or not? So we can use specific capacity. So during our preliminary testing, we can calculate specific capacity. And from that, there are some calculations to estimate transmissivity. Once you have transmissivity, then you can calculate hydraulic conductivity, and which is transmissivity is really hydraulic conductivity times aquifer thickness, and we're assuming we know our aquifer thickness. And so we can actually break these parameters out based on specific capacity, and then we can calculate our discharge based on the time equation. And that's going to give us, at certain drawdowns, it's going to give us our flow rates, and then we can estimate the zonal flow from that. So we're not going to go into all the calculations involved here because it can be expensive. We get into a whole pumping test discussion and how to calculate these things. There is software to model all these things up. So for the most part, if you really want to understand the dynamics, you look at a pumping testing book, and that'll tell you what's going on there. Mass balance for water quality. This is kind of a simplistic weighted average. So we look at our specific zones. So we for each zone we look at the discharge. So the flow rate, that would be in zone 1, that would be Q1. Concentration of contaminant would be C1. And then for each zone we do the same calculation. We add all those up, and then we divide for all our different zones. So QN, CN is actually the, if you have fourth and fifth zones, then you're adding all that up. And then we're going to divide by our flow total, and that's going to give us our weighted average concentration. So in this case, we have 3 zones we're testing. We have arsenic in the first zone, 9 micrograms per liter, or parts per billion is what that is. 5 micrograms per liter in zone 2 and 20 micrograms per liter in zone 3. Our flow is 200 gallons per minute, 450 gallons per minute, and 150 gallons per minute. If we do if we add up our flow, we get 800 gallons per minute. We do our calculations, we come up with our average arsenic concentration is 8.9 micrograms per liter based on our testing. And obviously, you can take this is kind of a simplistic look at the total average, or the weighted average in the well itself from all our zone testing. And you can start to look at these calculations and determine if we have high arsenic zones. We need to look at things and say, okay, how do we improve things if we took out zone 3 here? It's 20 micrograms per liter arsenic, but it's only 150 gallons per minute. So if we take that zone out, we lose 150 gallons per minute, but how much do we gain in dropping down our arsenic concentration? So right now we're running at 8.9, which is, pretty much 9 micrograms per liter, which is just 1 shy of the MCL. Kind of a little too close for comfort. So in this case, we may look at at sacrificing that 150 gallon a minute zone and to knock our concentrations way down, and so we don't have to look at potential treatment or additional monitoring. So you can start to see how this might work out. There's some more complex calculations we can do to look at the zonal contributions based on the flow for each one of these zones, and then we can adjust the thickness of the zones and adjust our screen and play with this a lot of different ways, but you get the picture here of how we do these calculations, and that's kind of what we're doing in the field. And then we'll take our zone test or well profile information. That's where we'll make our final well design decisions, and then do our well construction based on those decisions. So, all right, so putting it together, mass balance calculations can be used to determine whether low quality zones can be sealed off. We want to evaluate the data to optimize well flow versus water quality. So it's going to be kind of a balancing equation. We're going to do an iterative process to determine how much water can we get at what water quality. And we may be able to actually minimize or even eliminate treatment requirements if we do this right. We may need to sacrifice some flow in our well, but if we eliminate the need for an expensive treatment plant, then that can be well worth it. And so that's a decision that needs to be made based on the data. How much of an improvement can we make? All right, so let me just show you some montages here from our partner. We use RAS, Real-Time Aquifer Services, out of Denver, Colorado, to do our well profiling. That's our main partner, and they do excellent work. Highly recommend them. These are some montages that have been created for a couple different wells here. This is the well that I showed you earlier that I showed you the zone test configuration on. This is actually doing well profiling on that particular well. So we got our data up above, and I have to do a screen share on this because I can't fit it all on a regular screen. But you can see our column here off to the left is our E-log. So we have our geophysics. Over there on the far left, we have our gamma is in red. Our SP, spontaneous potential, is in the black dashed. The second column there are short resistivity and our long resistivity. The long resistivity is the dotted line, and the short resistivity is a solid black line there. You can see right around 50 feet or so, we had some glitches in the E-log, so not quite sure what happened there. Then we move to the middle. We're looking at our ambient flow conditions. So you can see that we have most of the flow coming into the well up above, and then off to our the actual flow is the black line here. Off to the right here, we have our pumping conditions, and you can see that under pumping conditions, we actually have quite a difference between the upper and lower part of the well here. So that's really showing us a lot between the ambient flow and the pumping conditions. So we see that most of our production under pumping conditions are from the upper part of the well here. And so we go down here and we see that we do get some zones down below where we got some water coming in here. And so that's all good. And you can see a bump in the resistivity over here too. We are then looking at the flow summary here in this column here. And you see the summary, our greatest flow is right in here, and then down around between 180 and 190 feet. So that's that peak there. Interestingly enough, not a real distinctive peak on the resistivity log, but that therein is our flow, and you can see on the ambient flow, which would be the where the the resistivity would be measured under non-pumping conditions. You can see it's fairly flat there, but under pumping conditions, this is the most productive zone in the well. So, and then we look at here is our arsenic concentrations observed and estimated. Observed is the red, and estimated is in the green. So we can see we have, our highest arsenic is right above this zone. We could have fiddled around here a little bit with the well screens, but the operator decided to take it all and do some blending as treatment. And because the arsenic is fairly uniformly distributed, there is a high zone right in here, but it's unfortunately right around where we have our most productive zones. So it really would not have been great for us to try to screen off maybe this particular zone here, but they opted not to do that. So there you go. That's one well. Let's look at our next one here is, bear with me, I'm doing a screen share here. This is a very shallow well here. Hold on a minute. Very shallow well. So the final constructed well ended up being about 80 feet. And so it was kind of tough to judge this one. We really didn't run quite as much. We ran ambient and pumping flow. We have our electrical logs, and then our well construction summary is here. And then we ran a lot more water quality data here. So this is really what this is looking at. This particular montage has, it shows we ran a couple different drawdowns here at different pumping rates, so you can see what the drawdowns were during those particular pumping rates. So a lot of information here. As we go down, we can look and see that pretty much all our production in this well is from the top of the well, and we do have some hit in what is that? That's I believe that's TDS up there. So no, that's something else. I'm not sure what that is. That may be sulfate up there. So yeah, I believe it's sulfate. So I think that's sulfate. I'm not sure. That may be hexchrome. Okay, I'm not sure on that one. It's the legend is a little bit hard for me to read right here, but you can see we did some specific interval testing here. We did a couple zones here. You can see markedly different water quality down below. Our TDS was way high, and our flow is actually down. Not a whole lot of flow down there, so we decided to screen that zone off and actually construct the well from 80 feet up. So a very shallow well, but as you can see in our flow meter data, most of our production is by far and away in the upper 50 feet or so of this well. So we actually had to get special considerations to build this well with a really shallow seal in order to take this zone, because California, the minimum seal is 50 feet. You can see that a big difference between TDS up above and down below. So TDS 1800 down below, 270 in this zone. So we're actually looking at a fair difference in TDS. We decided to leave that water down there and just build the well here. So, and that proved out that our flow was actually coming from up there. So that was not a hard decision to make. So there's a couple examples conducted by Real-Time Aquifer Services, and that's kind of what that's kind of the wrap on that. Obviously, there's a lot more detail. I mean, we teach some classes that are 3-4 hours long on this topic, so you can really get into the weeds with a lot of the geophysics. And one thing I didn't mention, when you're doing the well profiling, it's an opportunity to run some other geophysics. We'll typically run a deviation log, we'll typically run a caliper log, but you can also run some other tools as well to look at porosity and really look at the aquifer and get a lot of detailed information there. That wasn't on some of these logs I showed you, but you can get pretty fancy. In a fractured bedrock aquifer, you might want to go down with either an optical televiewer or an acoustic televiewer. Certainly, you're going to want to run a video of some sort on a fractured rock aquifer so you can identify your fractures, but using something like an optical televiewer can really give you a lot of data on the fractures, their orientation, and really help you dial in your well profiling, your Packer test, your zone testing, whatever you want it to be. So a lot of opportunities to do some different things here. I've showed you the basics, but you can let me know if you have any more questions, and we can certainly answer those for you. All right, so I did mention real-time aquifer services earlier. This is their contact information. They're our partners on these things. We use them pretty much exclusively for our well profiling needs, and they do a great job. Especially in the geophysical and the geologic interpretations, really quality work and a lot of detail there. They have a lot of the expensive tooling, so they can do a lot of different stuff here. Besides just the flow profiling, they have all this other tooling like the optical televiewers and that stuff, so you can really get a good look-see depending on the type of data you're really looking at. So we highly recommend them. There's their contact information. All right, so that's a wrap on today's show. I hope we gave you a little bit of an idea. Glitches aside, I apologize for that. Probably what I'm going to do is just have to record this or put it together and upload it as a full recording, because I got bumped off the internet a few times, so my apologies on that. I have no idea what went wrong there, but it is the internet after all. So, all right, a couple other things coming up. We do have a well health check class coming up. That is coming up June 8th. That's a 1-hour class on doing diagnostics on your well. We'll be looking for information on that. We're also doing a longer class. This is a 6-hour class done for 2 hours a day over 3 days. So in Pacific time, it's 8 to 10. So if you're a water system operator, you can take the class, get your contact hours, and still get out there and do your job for the day. So we've had good luck with that format in the past. So we're looking at July 12th to 14th for that particular class. All right. So you can find us on our streaming channels of the Groundwater Guy channel on YouTube and on LinkedIn at tballard.com, usually under my events. That's where the shows are. I live stream into both these channels. All of my recordings are up there on the Groundwater Guy YouTube channel, so check us out there. If you'd like to be a guest on the show, here is the contact information to do that. Just pop in there and schedule yourself up. If you've got a topic of interest to the water industry, I'd love to have you on the show as a guest. All right, thanks for watching. Don't forget to subscribe to the YouTube channel. If you want to know when I post new videos, hit the alert button. That is the Groundwater Guy YouTube channel. We will see you next week.